Can a system be dangerous, even if nothing is broken? In many cases, we focus on system failures. But what if the system works exactly as designed and still leads to a hazardous situation? This is where SOTIF comes into play. SOTIF stands for Safety of the Intended Functionality. It addresses risks that are not caused by faults, but by limitations in system behavior. And this is especially relevant for modern systems like ADAS and automated driving. In this video, we explain what SOTIF is, how it differs from functional safety, and why it is becoming increasingly important. Why does SOTIF matter? In traditional functional safety, we focus on system failures. A fault occurs, which leads to a malfunction, and eventually a hazard. But modern systems introduce a new type of risk. A system can behave exactly as intended, and still be unsafe. For example, a perception system might misinterpret the environment, even though all components are working correctly. This is especially relevant for systems like ADAS and automated driving. These systems rely heavily on sensors and complex algorithms, and their limitations are not fully covered by ISO 26262. This is exactly why SOTIF is needed. So what is SOTIF? SOTIF stands for Safety of the Intended Functionality. It is defined in ISO 21448. Unlike functional safety, SOTIF does not focus on system faults. Instead, it addresses situations where the system behaves exactly as intended, but still leads to a hazardous outcome. This often happens due to limitations in perception or interpretation. For example, a sensor might not detect an object correctly, or an algorithm might misinterpret a situation. SOTIF focuses on identifying these limitations and reducing the associated risks. And in this way, it complements ISO 26262. So, how does SOTIF differ from ISO 26262? The key difference lies in the source of risk. ISO 26262 focuses on system faults. A fault leads to a malfunction, which can result in a hazard. SOTIF, on the other hand, focuses on situations without any fault. Here, the system behaves as intended, but due to performance limitations, it may still lead to unsafe behavior. For example, a perception system might misinterpret the environment. So the cause of risk is fundamentally different. But both standards are complementary. And in modern systems, especially in ADAS, both must be considered together. Let's look at a typical SOTIF scenario. Consider an ADAS system that uses a camera to detect pedestrians. In the real environment, a pedestrian might be partially visible, for example in low light or behind an obstacle. The system processes this input, but misclassifies the object. Not because of a fault, but because of a limitation in perception. As a result, the system may react too late, or not at all. This can lead to a hazardous situation, even though the system is working as intended. And this is exactly the type of problem that SOTIF addresses. So where do SOTIF risks actually come from? There are several sources. One important factor is sensor limitations. Sensors may not detect objects correctly, especially under difficult conditions. Environmental conditions also play a role. For example, poor lighting, weather, or occlusions can affect perception. Another source is algorithm limitations. Even advanced algorithms are based on assumptions and may not handle all situations correctly. This is especially critical for AI and machine learning systems. If the training data is incomplete, the system may not recognize certain scenarios. And finally, there are edge cases, rare or unexpected situations that were not considered during development. All these factors contribute to SOTIF risks. So, how can SOTIF risks be addressed? One key approach is scenario-based analysis. This means identifying relevant real-world situations that the system must handle. These scenarios are then tested, under different conditions. Extensive validation is essential, especially for perception systems. Another important aspect is improving the algorithms. As new limitations are identified, the system must be refined. This also includes enhancing the training data. More diverse and representative data helps improve system performance. And finally, continuous monitoring is required, because new situations can always emerge. So addressing SOTIF risks is an ongoing process, not a one-time activity. What challenges arise in practice? One of the biggest challenges is defining all relevant scenarios. Real-world environments are extremely complex, and it is difficult to cover everything. Testing is another major effort. To validate system behavior, a large number of scenarios must be evaluated. Edge cases are particularly challenging. These are rare situations that may not occur frequently, but can still be critical. Data also plays a key role. If the training data is incomplete, the system may not perform reliably. And finally, there is always a trade-off between performance and safety. Improving one aspect can sometimes impact the other. There are several common misunderstandings about SOTIF. One of the most common is the assumption that SOTIF is the same as ISO 26262. But as we have seen, they address different types of risks. Another misconception is that no fault means no risk. In reality, a system can behave exactly as intended and still be unsafe. Some also believe that SOTIF is only relevant for AI systems, but it applies to any system with perception or interpretation. Another common belief is that testing alone is sufficient. But addressing SOTIF risks requires multiple strategies, not just testing. And finally, SOTIF is not optional in modern system development. Let's summarize the key points. SOTIF addresses risks that occur without any system faults. It focuses on limitations in perception and system behavior. This is especially relevant for modern systems like ADAS and automated driving. ISO 26262 addresses faults and malfunctions. SOTIF complements this by covering risks beyond failures. Together, they provide a more complete view of safety. And addressing SOTIF risks requires continuous analysis, testing, and improvement. If you want to go beyond this introduction to SOTIF, we offer comprehensive online training programs on our website. These self-paced courses cover ISO 26262, SOTIF according to ISO 21448, as well as detailed topics like HARA and ASIL. The focus is not only on understanding the concepts, but on applying them in real engineering projects. You can find the link in the video description and also in the pinned comment below. If you found this video helpful, feel free to give it a like and subscribe to the channel. We regularly publish content on functional safety, cybersecurity, and automotive engineering standards. Thank you for watching, and we look forward to seeing you in the next video.